Okay, let's get started, please. So we're talking about the logarithm. Can anybody tell me what, just as a warm-up, what does the logarithm mean? What does log base b of x mean? Anybody remember what this means? There are a couple of ways you can say it. You know, anybody? No? Yeah, Jane.
It's equal to the power you raise b2 to get x.
The power, yeah. So that's a good way of thinking about it. The power 1 raises b2 to obtain x. Right? Right, and it's, I should emphasize that it is the unique power, right? There's no other power that you could raise b2 to obtain x. So if I have something like log base 10 of 100, right? Then when you see that, you say, oh, that's going to be the power I raise 10 to get 100, right? What power do I raise 10 to get 100? Well, it's 2, right? So this would be 2, right? If I say log base 10 of the square root of 10, right? Well, that would be 1/2, right? Because this is 10 to 1/2, right? Log base 10 of 10 to the x. What would that be? X, right? Because it's the power you raise 10 to get 10 to the x, right? What power do you raise 10 to get 10 to the x? Well, just x, right? Okay, so yeah. Okay, and this actually leads into the other way of thinking about the logarithm, maybe the more official way of thinking about the logarithm, that the log base b of x is the inverse function of b to the x, right? It's the function that when you compose it with this, right, so it's the, right, so this is like thinking of this as a value. As a value, it's the power you raise this to. But thinking of this as a function, it's the inverse function to b to the x, right? So you know that log base b of b to the x equals x. You know that b to the log base b of x equals x. Right? And like we said last time, this is basically, the second one is basically saying this. Right? B to the log base b of x is x, right? This thing is the unique power that you raise b2 to get x. Okay. Let me have you do a couple on your own, just to wake you up. Log base 9 of 27. Log base 4, so these are a little tricky. Log base 4 of 1 over 32. Log base 5 of 5 times the square root of 5. Okay, so take a minute and see if you can get those. Probably the easiest one is the third one. So if you're if you're getting lost, start with that one and then do the others. What time is it? 7:08. Okay, talk to somebody. Okay. Would somebody like to try the third one? Would somebody like to try the third one? I can, if you want, I can lead you through it. Anybody want me to lead them through it if they're feeling a little shaky? Yeah, sure.
No, can you read it as?
Yes, absolutely, absolutely. So you think, what does this mean? This is the exponent you raise 5 to, right? To get 5 times root 5. Okay. That's what that means, right? The exponent that you raise 5 to, that's how you read this, right? The exponent you raise 5 to get 5 times root 5. So what do you need to do? What power do you need to raise it to get 5 times root 5? So thinking about this in terms of exponents, well, 5 is just 5 to the 1, right? What about root 5? What's that using an x? Can you express that with an exponent? No? That's actually going to be, that's the square root of 5, so it's 5 to the 1/2. That's okay. So 5 to 1/2, right? And so altogether, that's going to be 5 to the 3/2, right? Because of properties of exponents, right? So remember that 5 to the a times 5 to the b is 5 to the a plus b, right? 5 to the a to the quantity b is 5 to the ab. So these are the, in case you've forgotten, these are the basic properties of exponents. These are basically the only properties of exponents that you need to know. Okay. These are the main properties of exponents. Okay. So we use that first property, that a base to a power times a base to a power is the base to the sum of its powers. Okay. So so now we're asking, what power do we raise 5 to get 5 to the 3/2? Well, it's going to be 3/2. Right, because if we put in 3/2 here, we get, right? Our question was, what power do we raise 5 to get this? But this thing here is 5 to the 3/2. Right, this thing is 5, this is 5 to the 3/2. So we're asking, what power do we raise 5 to get 5 to the 3/2? Well, it's just 3/2. Right, so it's just 3/2. Okay. Similarly here, it's, what power do we raise 9 to? 9 to the what? 9 to the what? So thinking about this, it's 9 to the what equals 27. 9 to the what equals 27. And did anyone figure this one out? Anybody? Jenny?
Isn't it just 9 to the 3/2?
9 to the 3/2.
It's 9, 27 is equal to 9 times square root of 9, right?
9 times the square. Oh, yeah, sure. So you can say, oh, look, this is the same thing as 9 times the square root of 9. Right? it's 9 times 3, which is 9 times the square root of 9. Right? So that's again 9 to the 3 halves. And so the thing we're looking for is 3 halves. Right? Okay. Another way you could have seen that, I don't know if it's maybe less clever. You could say, well, look, this 9 is, we're looking for 9 to what power equals 27. Well, that's 3 squared to what power equals 3 cubed. Right? 3 squared to what power equals 3 cubed? Well, that's going to be 3 halves. Right? Because of the second property of exponents, right? Something raised to a power raised to a subsequent power is the product of the powers, right? So we want to have a 3 halves here so that we get 3 squared, 3 to the 2 times 3 halves, right? This is going to be 3 to the 2 times 3 halves, which is 3 to the 3, which is what we want. Okay. Okay. And then this one, did anyone get it? Yeah, Amy.
Not
Negative 5 over 2. So let's see. So let me think. So this is, we're asking 4 to what power equals 1 over 32. Yeah. How did you get it? I should ask you that rather than tell you, rather than say how I did it.
I made 4 2 to the power 2.
Yeah. So you got 2 to the power 2 to what power equals
And then 5, or 2 to the power negative 5.
2 to the power negative 5.
And
Right?
then 2x is equal to 5 minus 2.
Exactly. Yeah. So you say, okay, well, what do we need here? We need a negative 5 over 2. Right. So it's going to be equal to, the answer is negative 5. Anybody have questions about that? This is just, this is just some trickery done. Yeah, I wouldn't be too. This is a little bit contrived. This is a little bit contrived. This problem. But it does make you think about logs at least. Okay, let's see. There's a comment, one remark that's important. Log base e is usually written ln. Okay, so whenever you say ln, it means log base e. This stands for like natural log. Natural log. This n stands for natural. The l stands for log. And some people, physicists in particular, read this as lan. Yeah, I've heard people say this, but I don't like it. So, where's the a? Right? There's no a in there. But yeah, some people read this as lan. Okay. So another remark is that as we noticed before, these functions are like this exponential function. Say, let's pretend that b is bigger than 1, so we can draw it. This is a one-to-one. Is a one-to-one function, right? As is the logarithmic function is also right. They've got inverses. They have to be one-to-one, right? So what that means is that if b to the x equals b to the y, then x equals y. Right? If you end up with the same output value, you must have started with the same input value. Okay, that's what one-to-one means. Okay. So like, the reverse direction is always true, right? If x is equal to y, then b to the x is equal to b to the y, right? But it's only for one-to-one functions that the opposite direction is true, right? If you think, some of you look a little confused. So, like, if you think about the x squared function, right? If x equals y, then certainly x squared equals y squared, right? right? But if x squared equals y squared, that does not tell you that x equals y, right? For the squaring function, right? Because the squaring function is not 1-to-1. Okay. Okay. So yeah. So b is 1-to-1, which means that this equality is equivalent to this equality. Okay. This equality. These equalities are the same equality. They logically imply each other. Right, and similarly, the same thing for the log, right? Log base b of x equals log base b of y if and only if x equals y. Because of the one-to-oneness. And we can use that. To change, to solve exponential equations. Okay. So here's an example. Somebody says e to the 2t minus 5 equals 5,000. Okay, e to the 2t minus 5 equals 5,000. What is t? Okay. Now, this equation, the thing that you're looking for is in the exponent, right? The thing you're looking for is in the exponent. How do you get it out of the exponent? Well, we can apply log to both sides. What we're going to do is we'll hit both sides with the log. So we'll say, okay, and I'll use natural log because I've got this e here, right? So I'll say this equality is the same thing as this equality. Right? So I just take that original equality and I change it into I hit both sides with the log. Okay. Now, what's natural log of e to the 2t minus 5? Write down something, take 10 seconds, write down what this left side. This right-hand side we're just going to leave. It's just natural log of 5,000, whatever number that is. But on the left-hand side, what is this? Take 10 seconds and write something down. Hopefully that should be screaming at you, screaming something at you. Say something to your neighbor. What is it? 2t minus 5, right? What's the screaming going on here? It says inverses, right? These are inverse functions. Natural log of e to the blah, right? Those cancel each other out, right? Natural log of u of the x is just x, right? Because those are inverse functions, right? So you get 2t minus 5 on the left. And then you've got this plain old equation that anybody could solve, right? So t has to be natural log of 5,000 plus 5 everything over 2. Okay. So you've taken this equality, which seemed kind of confusing maybe, and just changed it to its logarithmic equivalent statement, right? It says log of 5,000 equals 2t minus 5, and then you just solve. Okay, here's another one along those lines. Okay, yeah, here's a good one. Okay, money grows. Not that money is everything that you want to be thinking about, but in any case, money grows like a naught e to the rt. So at time t. Okay, where this is your initial investment. My father is an economist. So when I was growing up, this is back when I was a kid in North Carolina, my dad actually had us graphing stocks. I didn't really know what was going on, but like every day he had us look in the newspaper, and I was supposed to keep track of some stock, and so we had graph paper, and he'd say, okay, every day put a mark where the at the stock price. Yeah. Nowadays you can get that on the computer pretty easily, right? Years and years of data, right? But in those days, this is how we did it. Like child labor. Yeah, so I kept track of one stock, storage technology. It's like some sort of old, ancient computer storage storage stock. And my brother kept track of Quantex. I'm not even sure what that was. Anyway, yeah. So this is money in a bank actually grows at a like an exponential function, where this is your initial investment. So if you have $10, you put that in the bank, it's going to grow at a certain exponential rate. This R basically is the interest rate. So when does your money double? Right? At some point, it's going to become double. Okay. The question is, when does your money double? So when does your money turn into 2A naught? Right? You started out with A naught. At time 0, you got A naught. Right? You notice that P at 0 is A naught e to the 0. Well, that e to the 0 is just 1. So at time 0, that's your initial investment. At what time do you end up with twice your initial investment? Okay. See if you can work it out, right? When does this equal twice your initial investment? For what t does this happen? Right. Here is your exponential equality, and you want to solve it. Okay. Take a minute, 2. That was actually almost 50 years ago that my dad had us doing this. It's a long time. I've lost my North Carolina accent, as you say. Okay, turn to your neighbor. Talk. Okay. Anybody want to tell me how they did it? What they did? Anybody get the answer? No? So let's think. We want, what do we want? We want t such that a naught e bar t equals 2a naught. Okay. Let's make that a little simpler and just divide both sides by a naught, right? We can multiply by 1 over a naught on both sides. So we want t such that e to the rt equals 2. Right? So we have this exponential, right? We have this exponential equality, and what are we going to do with it? Sorry? We hit it with the natural log. Natural log, that is the natural log of 2, right? Screaming occurs, right? And we end up with RT equals natural log of 2. Right? In other words, the time to doubling is going to be natural log of 2 over R. Okay. Natural log of 2 is like 0.693, around there. Okay, so for example, if your investment had a 10% annual rate, then that would mean that that it would take about 7 years, to double. Right. So that's, historically, up until recently, they were saying that the stock market on average gives about 10%, about a 10% return. Nowadays, it's about 6%. So, slightly less than double this, maybe 12 or 13 years to double. Yeah. So that's actually pretty interesting because, then you can think when you make an investment, what I do is think about like doubling time. Like how much doubling time is there until, for example, retirement? If you're saving money for retirement, you think, okay, and this, I don't know if you want to think in this way, but when I was in my 20s, many years ago, I would say, do I want to spend this $10 now, or calculate, right? I think about how many doublings, like maybe at that time it was, I had, so I was in my 20s, so like 40 plus years till retirement, right? So now 40 plus years is like 6 doublings, right? 6 doublings is 64, right? 2 to the 6, that's 64. So you think, okay, do I want to spend this $10 now, or do I want $640 in retirement? And then I wouldn't spend the $10, right? Or now that I'm older, I sort of feel like it's not that many doubling times. I feel a little bit more willing to spend money now that there's fewer doubling times. But anyway, when I was younger, I was very, very stingy. Okay. Yes.
Question.
Yes.
Can you refresh what natural log is?
Natural log is just log-based e. So it's a logarithm function that's the inverse of the e to the x function. And remember, e was that special number, like 2.7181828. It's just the log that we use most often. Yeah. It's probably more intuitive for you guys to think about log-based 10, right? Because you've got the 10 fingers and all, and our number system is based on 10. But for reasons that will not become clear until you take calculus, E is actually the best one. tempted to waste time by telling you the story of how a student dropped my class when I first started teaching. A student dropped my class because of my accent. Should I tell you this story? This is kind of interesting. So yeah. So do I have an accent? Or if I do, what kind of accent do I have? Okay. So yeah, I was born in North Carolina. I grew up in Virginia. I went to college in New Jersey, then graduate school in Chicago. Anyway, so when I was in Chicago as a graduate student, starting your third year, everybody has to teach courses, mainly calculus courses. And I'd been teaching for only a few weeks when the administrator in charge of the graduate student teachers came to me, and she sort of put her arm on my shoulder and she said, "Winston, I have to tell you that a student came to me today and said that he had to drop your class because he couldn't understand your accent." And I was like, I was born in North Carolina. Do I still have my North Carolina accent? And she said, she said, I told him that I know Winston O, and he doesn't have an accent, but he insisted. He said, no, he has a very strong Chinese accent. And so she let him drop the class. So. Now the interesting thing is that I had a friend who was in ecology, evolution, and biology graduate student. And she had some students who were common. And she talked with them, and she said, and these students were from Korea, and she said, does Mr. O have an accent? And they said, yeah, but we're from Korea, so we understand. So yeah, it's kind of interesting. Yeah, it could be some sort of. Some years after that, I saw that there had been some linguistics experiment where they took a person, they took videos of, like, say, a Chinese student and an American and a white student, and they dubbed them over with each other's voices. Okay, so they were actually speaking. The Chinese student was speaking for the other guy, and vice versa. And oddly, still, the people said that the Chinese student had a Chinese accent and the American student had no accent. So there's some psychological thing going on there. Anyway, I wish I had my North Carolina accent. But it comes out if I'm with people from North Carolina, oddly, after almost 50 years. Okay. Okay, let's go on to 5.4, properties of logarithms. Yeah, I haven't told you guys many stories, but I've got all sorts of kooky stories, like being stalked by a woman who thought she was a vampire. Did I tell you guys that one? Okay, I told you. Yeah. Did I tell you the one where I was mistaken for a spy? No, okay. No. At one point, I was basically fired from scripts, and then the day after that, I was awarded Professor of the Year. I'm still here, but that was not pleasant. I seem to be the kind of person that things happen to. Yeah. Okay. Okay. Properties of logarithms. There are two properties, just like there are two main properties, and this is not a coincidence. This is actually because of this. Because there are two main properties of exponents, there are two corresponding properties of logarithms. Okay. And they go like this. That the log of a product is the sum of the logs. Right? And the log of a power is that power times the log. right? And you think about it, you know, let's think about it. If let's try to change these things into exponential state. Let's exponentiate both sides and see what we get. If we say over here, b to the log bxy equals b to the log bx plus log by. Okay, let's take that equation and then, convert it to its exponential form and see what we get. Well, what's this? B to the log base b xy. Right, got b of log base b. B to the x composed with log base b. Right, so they cancel each other out. Right, you get xy here. Okay, what about over here? What about over here? Well, using the property of exponents, this is the same thing as, right, using that, one of those properties of exponents, this is b to the log base b of x times b to the log base b of y. Right, so this thing on the left is xy, and this thing on the right is, well, what's this? You should be able to tell me, just like that. B to the log base b of x, x, and this is y, x, y, right? So all this is saying, this is just a translation, this is just a sort of an application of a property of exponents, right? So that's how you get this thing over here. Right? So this is a sort of consequence of the a to the x plus y equals a to the x, a to the y property. Okay, and similarly, this one is a consequence of the other property. Okay, I'll let you work that one out. But just exponentiate both sides, and you'll see that using the second property shows that this one is true. Okay, so I should say that the book gives a bunch of other properties, like log base b of b equals 1, but that one you know already for sure, right? That's all it's, what's log base b of b? It's the exponent you raise b to get b. So that's equal to 1, right? So, or like log base b of 1 is 0, right? Because b to the 0 is 1, right? B to the 1 is b, right? So there are other sort of like trivial properties that the book lists, but it also says things like log base b of b to the x equals x, but you know that, right? Because that's just the inverse statement. It says log base b to the log base b of x equals x. That's also the inverse statement. The only one that is a little bit maybe sophisticated is log to the b of p over q equals log base b of p minus log base b of q. Okay. But you can figure that one out. Back up. What's this space here? If we think about that, log base b of p over q, well, that's the same thing as p times negative, I'm sorry, p times q to the minus 1. Right? P over q is p times q to the minus 1. Right? And then we're just gonna use these properties, right? Log of a product is the sum of the logs. So I'm gonna write this as this plus this, right? Log of a product, right? We've got these two factors here. Log of a product is the sum of the logs. And then I'm gonna use the second property, that log of something to a power is that power times the log. Right? That's this thing here, right? If you have log of something to a power, you can pull that power out and make it a factor. Okay. So this property is just a consequence of these two properties. As long as you keep these two properties in mind, everything else is just, all those things are just consequences. Okay. Just to get these things more ingrained in your brains, let's do a couple of examples. So here's one, log base 10 of 70 minus log base 10 of 7. So these are from your book, actually. Like, simplify the following using these properties. And I'll do a couple just to warm you guys up. Okay. So this one, I'd say, okay, well, look, I'm gonna simplify it by recognizing the 70 as 7 times 10. Right? 70 I can rewrite as 7 times 10, right? And then I'm going to use the log of a product as the sum, right? So I write this as the sum of the logs, right? Log of the product is the sum of the logs. Okay. But we have this log base 10 of 7, and we have a negative log base 10 of 7, so those cancel each other out. And we're left with log base 10 of 10. But what's log base 10 of 10? 1, right? So the answer is 1. Okay, so that all simplified to 1. I think somebody told me that most math problems you can guess that the answer is 1 or 0. Okay. Here's another one. 2 to the log base 2 of 5 minus 3 log base 5 of the third root of 5, the cube root of 5. Okay, I'll let you all try that. Okay, what's the answer? Anybody got an answer? Zoe?
No,
4? Let's see. So 2 to the log base 2 of 5, what happens to that?
5.
Just 5, right? Because you've got 2 to the blah and log base 2. right? Those are inverses of each other, so they cancel. Being 5. Okay. What about over here? We have log base 5 of 5 to the 1/3 power, right?
Yeah, that would be 1/3.
So that would be 1/3. Yeah. Right? So you get log base 5 of 5 to the, it's 5 to the 1/3 power, but you can pull that 1/3 out. You get 1/3 there. So you get minus, and log base 5 of 5 is just 1. Right? So you get 5 minus 1, which is 4. Thanks. Great. Okay. Let me do one for you. So here's an example. Log base b of 4 plus 3 times the quantity log base b of 1 minus 1 plus x minus 1/2 log base b of 1 minus x. Okay. So I don't think this is going to become very simple, but at least we can use the properties of log on it. Okay. So what I'm going to do here is that I'm just going to multiply everything by 3. So we get 3 log base b of 1 plus x minus 3/2 log base b of 1 minus x. Right? And here we've got log base b of 4. Log base b of 4. Right? So I'm just doing that's just arithmetic, right? I multiplied the 3 through. Right? Okay. Now we use the second property in reverse. So we can put this in as an exponent. So this is going to be log base b of 1 plus x cubed. And this is going to be minus log base b of 1 minus x and 3/2. Okay. Now I've got a sum here, right? I'm going to use this thing in reverse, right? Sum of logs is the log of the product. So this is going to be log of the product 4 times 1 plus 3 quantity cubed. And then I just got minus log base b of 1 minus x to the 3/2, right? And so then I'm going to use that p minus q property, right? And change this into log of this thing divided by, because I've got a minus here, right? So this is going to be this minus that, this over that, right? In other words, I'm putting, you can think of this as a plus with a negative exponent here, right? Plus the negative exponent, and then you multiply, sum of logs is the log of the product again. We end up with this. Okay. So this is kind of taking a bunch of terms and combining them, using properties of the log to combine them into one grand term, right? We could have just as easily assigned the opposite problem. Like, we give you this, and then say expand this out into simpler terms, into smaller terms, and then you would have had to go backwards up to something like this. Okay. Either way, you should try to be comfortable with using properties of logs to do whatever you feel like, either to combine them all into one grand term or to break them up into a lot of simple terms. Right? This is what the log is used for. Okay, that's it for today. See you guys next time.